Oh no, we're good. Everyone else is okay. Blue. I've got somebody that has 2 dark blue dice. You're good. 2 dark blue. Austin, here. Trade 1 for 1. Oh, I should have brought that in. I was never an infielder. I should have dove for it. And I think we're golden now. Yes. Actually, you need some dice. You were orange, so there you go.
I think those be separate colors.
They are, and the reason is on most of the dice, Tabitha, there's different numbers on the 2 different dice. Oh, so you need. Hang on a second. Yes, you do. No, wait a minute. Light color maroons. Should look like that. Oh, 2 light red, 2 dark red. Check that. It was straight across. I didn't think to check that. Yeah, that's perfect. So everybody has 2 different colored dice, right? They should be the same color, different hues. Who you work with, Jesse? Ashley, she's got dice now. You're good. You guys triple up. That's fine. Perfect. Perfect. Bueno. So everybody's got 2 different, slightly different shades of dice. Fantastic. What did I have you do on Wednesday? Do you remember what we did with these dice? Oh, making me happy, Cassie. You're making me happy. I had you come up with the frequencies of the different sums you could get on those dice. This is a fair pair of dice. A typical 1 through 6 on both dice. That's what would happen. On average, you're going to roll a 7, plus or minus 2.42. Okay? On average. But those dice that you have don't look like this. I screwed them intentionally. Blue dice, that's the distribution the blue dice look like. Very, very skewed. Very, very skewed. Trimodal, if you will, but definitely skewed. It's got a little bit of a higher average because more of the stuff's over here. And you've got about the same standard deviation because the spread's about the same, especially because most of the data is on the right. Yellow dice, my friends with the yellow dice, that's what your distribution looks like. It's kind of like the inverse of the blue ones, ish. Notice the lower average, which hopefully corresponds in your mind to the fact that you've got so much here, but the tail is pulling it this way. So hopefully that makes sense. Good. Here's your green. I call it the flip of the bird distribution. It's got an average of 7 because 7's right in the middle. But check the standard deviation. You see how it's wider? It's almost 3, where the previous ones were almost 2. Why is it so much wider? Why is this one's standard deviation wider than the previous 2s? Say that again. Yeah, you've got these goofy right and left outlier that are really stretching. If you think back, and of course this is asking you to think back about 7 weeks, there was a homework problem where you had to use an Excel spreadsheet to explore the maximum standard deviation in a data set. And the way to make that maximum was to pull the data points all the way to the outside. That puts the average in the middle, and it maximizes the standard deviation. So, cool so far? All right, here's the orange one. This was a fun one just because it's so goofy. You got two modes and a bunch of gaps. You got this goofy, meaningless average, essentially. Plus, about the same standard deviation as the first 2. And then this guy has the smallest standard deviation and the highest average. Because essentially what I did was I made it impossible for you to get the low sums. I made the numbers so high so they were all on this side. Fair enough? Excellent. Now the question is, I asked you to find mu and little sigma in a distribution. Why is that a little bit fictitious? In general, not for a pair of dice, but in general, Tabitha.
Isn't little sigma the full population?
Oh, yeah, makes me so proud to hear that. Little sigma is the population standard deviation, and little mu is the population's average. So in order to know little sigma, you've got to know little mu. No problem. Let's go get little mu. What's the problem with going and getting little mu?
You can't test everybody.
You can't test everybody. Now, I handed you a pair of dice. Obviously, you can. You just keep turning them until you see all the sides. Done. The problem is, suppose you wanted to know what the average BPA level is in someone who consumes water in a non-BPA-free bottle. How are you going to get that data? If you want mu, how are you going to get that data? I made Tabitha look, I'm sorry. Didn't mean to. You gave me that idea when you took the drink out of that analogy. How are you going to know if you want to get mu? Start asking, or start measuring, actually not asking, but measuring, right? Start measuring their BPA levels of every single person who's consumed water out of a BPA bottle. You see what I'm getting at there? Can you do that? You cannot do that. That is ridiculous. Think about everybody who's consumed water out of a BPA bottle. You can't do it. And in the time it takes you to try, more will have done it. And some of the ones you measured will have died, just by old age or natural causes. So the population is constantly shifting, so what do you do instead? You take a sample. Now the problem is, mu and sigma are population measures. What I want you guys to do is I want you to figure out mu, and also, just for grins, sigma, but through sampling. not through counting the sides of those dice. So in other words, you're going to start rolling the dice now. This is what the in-class quiz does. And you're going to use the results from the rolls to figure out what mu and sigma are, rather than counting all the sides. So essentially, you're going to do the same thing you just described to me. You're going to take a sample. It kind of make sense? We're going to find out here. 25 total, well, 100 total broken into 25 groups of 4. It's not as bad as it sounds. It's not as bad as it sounds, guys.
Are we using F9 or are we doing it for real?
You're doing it for real. It makes it, we're going to use F9 eventually, Corey. It's a great question. We're going to use F9 eventually when we start increasing the sample size. I promise you there. But this is more fun tactily. I promise you. Let me get the quiz out.